Okay, this is a video for Chapter 1, Section 1 for Preacalculus, and we're looking first at what is Chapter 1 about. Chapter 1 is all about functions and graphs, which is pretty much a broad category of a lot of stuff, but let's look at an overview. So in this chapter, we're going to begin to study the functions that we will continue to study throughout the book. And specifically, there's going to be about 12 different kinds of functions, and we're going to look at all sorts of different characteristics of functions. So your previous courses have introduced you to some basic functions. These functions can be visualized using a graphing calculator, and their properties can be described by using the notation and terminology that will be used and introduced in this chapter. A familiarity with this terminology will serve you well in later chapters when we explore properties of functions in greater depth. So we're doing a video for Section 1.1, Part 1, which is all about different kinds of modeling. There's three major kinds of modeling we want to look at: numerical, so numbers, algebraic, and graphical. So we're going to start with the simplest one. Numerical models. So scientists and engineers have always used mathematics to model the real world. So when we mean modeling, we're talking about the real world. And thereby unravel its mysteries. A mathematical model is a mathematical structure that approximates phenomena for the purpose of studying or predicting their behavior. Thanks to advances in computer technology, such as the Desmos program and graphing programs like it, the process of devising mathematical models is now a rich field of study in itself, mathematical modeling. Although this is a simple graphing calculator, there's definitely more powerful ones available. So we will be concerned primarily with three types of mathematical models in this book: numerical, algebraic, and graphical. Each type of model gives insight into real-world problems, but the best insights are often gained by switching from one kind of model to another. Developing the ability to do that will be one of the goals of this course. Okay, so we're going to start with a numerical, which is pretty much the sort of first level, the basic. You're looking at data, you're looking at numbers, and you're analyzing those numbers to gain insights. Okay, so let's look at our first example. So with a numerical example, you're given a table of some kind. So this is an example in your book. So we're looking at table 1.1, and every table has a title. Okay, so we're looking at the minimum wage, and we have a time period, and then we have a minimum hourly wage, and then we're looking also at purchasing power in 1996 dollars. So just general things, just looking at it, we can see that the years are going up by fives from 1955 to 2005. Our minimum wage is rising, and our purchasing power is, well, it starts to rise, it's going up, it's going up, it's going up, and then it starts to go down, and then it kind of goes up a little again and it goes down. So it's not exactly linear. So in the book, we're looking at this example to answer some questions. So we're tracking the minimum wage. The numbers in Table 1.1 show the growth of the minimum hourly wage from 1955 to 2005. And the table shows the minimum hourly wage adjusted to the purchasing power of 1996 dollars. Using the CIP, okay, we don't have to read all that, blah, blah, blah. Answering the following questions using the only the data in the table. Okay, so we're just looking at a table is how a numerical example essentially works. A, in what 5-year period did the actual MHW increase the most? Okay, so we're looking at biggest increase. So we see like 25 cents. Another 25 cents. Then from here we go up 35 cents. Then from here we go up 50 cents. Ooh, there's a contender. Oh, never mind. There's $1. And then from this one, we're back to 25 cents. Then we are at 45 cents. And then we are at, let's see, another 45 cents. 75, 90 cents. And then nothing. So our biggest increase was from the year 1975 to 1980. We went from $2.10 to $3.10. So we grew $1 from 1975 to 1980. Next, in Part B, we're looking at in what year did a worker earning the minimum hourly wage enjoy the greatest purchasing power. Okay, so we're looking at the greatest purchasing power column, which is our third column. So let's see here. Our purchasing power, we have 439, 530. So our biggest number that we ended up with was 647 through all of these, which was in 1970. C, a worker on minimum wage in 1980 was earning nearly twice as much as a worker working minimum wage in 1970, and yet there was a great pressure to raise the minimum wage again. Why? Well, oops. Let me just change the color. So let's compare these two. We have 1980. No, that's not the color I wanted. So 1980. Let's look at the purchasing power. This was when we can see the purchasing power was really dropping. In 1970 was at its highest. So probably because of this big increase, this $1.50 increase over 10 years was really because things were dropping. Okay, purchasing power is essentially how much you can purchase for your dollar, or something along those lines. It's really the value of your money. So we can essentially see that the purchasing power was dropping, and that's the reason. So something along the lines. So the purchasing power dropped 57 cents in this period. You can see the more exact answer in your book, but okay, let's look at an algebraic model. So algebraic, you want to think equations, solving equations, but we're not talking about graphing yet. So an algebraic model uses formulas to relate variable quantities associated with the phenomenon being studied. The added power of the algebraic model over a numerical model is that it can be used to generate numerical values of unknown quantities by relating them to known quantities. So we're going to look at example 3, which is comparing pizzas. So a pizzeria sells a rectangular 18 by 24 inch pizza for the same price as its large round 24 inch in diameter pizza. If both pizzas are of the same thickness, what option gives you the most pizza for the money? Well, since the thickness is not going to matter, we don't know. I mean, that's not something we know, but it's not something we need to know. All we need to know is that they're the same. So for a rectangular pizza of 24 by 18, we're just going to do a very simple equation using the formula for the area. So area equals 18 times 24. We multiply that out. And you get 432 square inches. Then we do our circle. Remember, for area of a circle, we don't need the diameter, we need the radius. So the radius is 12. And notice also that they should be in the same units. We are dealing with inches for everything, so we don't have to worry about that. But if you're not dealing with the same units, then it's not comparable. Then you need to convert units. Okay, so our area here is pi times 12 squared, 144 pi, which we're going to have to multiply pi out so that we can compare these numbers. 144 pi is about 452.4 square inches. So we can see that this is going to be the better deal since they're for the same price. You get more for this. Okay, then the graphical model. The graphical model is a visible representation of a numerical model. So we're looking at the graph, basically. And learning how to interpret that graph and learning how to interpret graphs in general is a major goal of this book. We've already seen a little bit of that. Okay, so here's the first example we're going to look at. Example 4. Visualizing Galileo's gravity experiments. So Galileo spent a good deal of time rolling balls down inclined planes, carefully recording the distance they travel as a function of elapsed time. His experiments are commonly repeated in physics classes today, so it's easy to reproduce a table of Galilean data. Okay, so here's our table. So again, we're starting with a table, but we want to identify a graphical model that goes with this data. So the first thing you're going to do is you're going to plot this data. Now we're not going to do it on graph paper. If you have a graphing calculator, you can do that in a graphing calculator, or we're going to use Desmos. So I'm going to show you how to use Desmos to do this. Okay, so I'm getting out of PowerPoint here. And so what I did in Desmos is I did a table. If you want to do a table, you have to go to Add Item and Table. So I copied this information that was in there, and then it'll plot it for you. And so you can see those purple dots. If you ignore the you're now using reserve battery power thing. There we go. Okay, so there's my dots right here. Now I can't see all of them. I plotted 9 dots. So it might be helpful to use the graph settings tool. We don't need the negatives in a problem like this. So I'm going to put that to 0. And I'm going to put this to 0. And maybe let's make the step along the y-axis, because look at our x-axis, it's going by 1s, but our y-axis is getting all the way up to 48. So it might be good to maybe go by 5s. Okay, but I didn't, 55. And now it's going by 5s. So you could do that. But that's going to skew your graph a little bit. So if you don't want to go by 5s, that's okay. We can go by 1s. It won't let me do that now. It likes the 5s because it fits. Well, let's go to 15. Okay. Now I'll go to 10. And I want to change this back to 1. It doesn't matter. whatever makes it easier for you to see the points. If you do change the way that the y and the x-axis are going, like if you make this one go by 5s and this one by 10s, then it doesn't quite work out. Okay, well, I'm going to zoom out until I see all my points. Again, I don't really need to see the negative, so I'm just going to move it over. So, what does this look like? If you're thinking, hey, that kind of looks like a parabola, you're right. It is. So now we need to do something that's on a graphing calculator. I think it's called a quadratic regression. But we want to find the equation, basically. So to do it on Desmos, I'm going to add an expression. And I'm going to type in y equals or f of x equals, it doesn't matter. And I'm going to type in the standard form of a quadratic. So ax squared plus bx plus c. And when you use a, b, and c, it's going to ask you for the sliders. And I'm going to choose all. So it gives you sort of a parabola. So I can see the vertex is at 0. So that means the c is probably going to be at 0. No, too far. No, when you do the slider, you can actually type in the number. I'm just going to let c be 0. And then the b. So what I'm doing is I'm trying to get the graph to match up to the points as much as possible. So as I go up on the b, it doesn't really help. It looks like it's at 0 too. Yeah. Now the c or the a determines how wide it is, or skinny. So if I go really, really skinny, it looks like this. If I go to 1, it looks like that. If I go to 0.5, it looks around there. So I need to go somewhere in between until I hit as close as possible to those points. So I'm at 0.7 right now. And so that's really, really close. I think, and 0.8 is close too. So it's somewhere between 0.7 and 0.8. And in fact, the answer is 0.75 is exactly the answer. And there you have pretty much an equation. B is 0, C is 0, and A is 0.75. And that is essentially an algebraic model that fits this graphical model.